So we have a triangle ABC and M is the midpoint. BC. D and E lie on the A bisector. So BD and CE are perpendicular to it. I feel like there's a lot of problems that have this kind of idea, where you have the two perpendiculars to the angle bisector. And then I wonder if these 4 points are like in harmonic conjugation, just because I feel like I've seen this idea a couple times. Okay. Prove that MD. Okay. So, oh yeah. So this problem I think we've done before. I forgot the proof of it, but I think it's very easy to show MD equals ME, right? I just forget what the idea was. Oops, sorry. So yeah, part one.
By the way, answering your question, AFDE is harmonic because you just projects from the point at infinity of a direction BD.
Okay, so you take BMC infinity and you project those. So what do you project through?
I project the bundle AFDE through the point at infinity of line BD.
Okay, and what do you project it onto? BC?
Line BC.
Okay.
You'll get BC and F and the intersection of BC and the external angle bisector of ABC. And that's harmonic.
Yeah. So with this. So yeah, basically you draw the intersection of this with BC. And then, yeah, and then those are obviously, these are a harmonic bundle, so that solves it. So yeah, so that shows that AFDE is harmonic, and then is there a way to see from there that MD equals ME? Well, actually, I think it's kind of obvious that MD equals ME because M is the midpoint of BC, so it has the same distance. Since BD and CE are parallel, it has the same distance to the lines BD and CE. So MD equals ME. So yeah.
Yeah, and there you use that BD and DC are perpendicular to A.
Yeah. In fact, yeah, I mean, really for any two parallel lines through B and C, like M is going to have the same distance to both. So, yeah, from there, it's not hard to see. Yeah, MD equals ME. Okay, so let's look at part two. We have a point X on the A bisector. And P and Q lie on the plane so that EQ is perpendicular to AB. And XQ is perpendicular to AC. EQ. And then DP is perpendicular to AC. And PX. Okay, so this is point P. And we have a bunch of right angles. And then we would have a point Q. Let me I want point Q to look a little better. So that's P. This is Q. Let's draw the feet of all these perpendiculars. So we have all these perpendiculars. The lines cross at P and Q like this, and let's make Q look a little better. Maybe something like that. And we want to show XM is the radical axis of MEQ and MDP. This is interesting. Yeah, it looked like a complicated problem statement, but maybe it's not so bad. So QJ and E. All right. So yeah, probably a lot of cyclic quads with all the right angles. AIXG is cyclic, that's obvious. I don't know if we want to let these right angles meet, but let's see, what's a good way to draw this? I like that. Yeah, MD equals ME. They're probably telling us that for a reason. We need to show X has the same power with respect to those circles. We have two trapezoids here and here. Oh, it looks like some people had to drop off. Oh.
I wonder what do we know about the circle that passes through D and E and has the property that MD and ME are tangent to this circle.
Passes through D and E, and MD and ME are tangent. Let's see, how would we draw that? So that would kind of mean thinking how we would draw that. Okay, so basically that would mean angle MDE would equal whatever that angle is. I guess one way that we could do it is like if we drop the perpendiculars to MD and ME so the circle that you just mentioned, I'll try to draw it. Oh, okay, so that would be, so the intersection of those lines would be the center of that circle. Is that kind of, yeah. What made you think about that circle? I wonder if these concur right there.
Well, we ultimately want to say something about the power of x with respect to the circles.
Yes.
And then here we have things like x is on DE, which is like polar of M. So M must be on the polar of X.
Interesting. And it looks like these concur also. So we want to show M lies on the polar of X. And let's see, if these concur, then something else has to concur. Then CE and this point also concur, I'm guessing. Although that doesn't look like it. So maybe not. No, because this is the intersection of two circles. Yeah, so this is where BB and JE intersect. Then we want to see where, okay, so maybe CE and HK intersect on this circle. Interesting. Glad you brought up that circle. Yeah. So it's almost like we have a rectangle here. And we haven't proven all this, but I think we'll be able to. Yeah, this is like a rectangle. And let's say we know all that. MD and ME are tangent to it. And that all exists like that. Okay, so we want to show that, well, if we know that circle exists, then we know M lies on the polar of X. So what's the other point of tangent C? Oh, is XN tangent to the circle? That would be interesting. I don't think it's true that XN is tangent to it. But okay, so we want to show that X has the same power with respect to these two circles. But how did you go from powers to like poles and polars? I forgot what you were saying.
Nothing. Yeah, particularly.
Like I thought you said something like yeah, I'm not sure. Well, if it has the same power, that means the length of the tangents to each of the circles is the same, right? Guys, I'll be right back. All right, I'm back. So M lies on the polar of X. I don't know what to do with that, but maybe there's a way to use Picard's theorem somehow.
Intersect those two circles, QME and DMP, with XQ and XP.
This and this.
Yeah.
Okay.
Then I think it's an angle chase to show that ODM and EMR are collinear.
Okay.
And since we want to show this radical axis thing, then it is enough to show that QORP is cyclic.
QORP. Okay. Interesting.
So, also, I found since DM is perpendicular to XQ, I think that is true, you can check it.
Yeah.
Then after some angle chase, I think we should prove that DOR, that triangle, DOR, is similar to EOH. Actually, no, EPQ.
DOR is similar to EPQ.
I think inversely similar. They are not oriented the same way.
But DOR is acute and EPQ is obtuse, right?
Okay, I probably made a mistake.
That's all right. Okay, so that's, yeah, adding in those points definitely looks useful. Are those circles tangent? They almost look tangent. So yeah, you were asking if it's a right angle. Looks, yeah, it's a right angle.
Could you check if DQR and EPQ are, since in my picture it does look like similar.
DQR and EPQ, or sorry.
Yeah. So check angle DQR and QPE.
So DQR and QPE.
No, DOR and QPE.
Okay. DOR and
EPQ.
EPQ. All right.
Okay, then I think that QER and OEP are actually similar. So I just made a mistake for 2 points. So check then if QER and OEP are similar.
QER and OEP. Okay.
That may be true.
So they both pass through P is kind of what you're saying, right? QER and QER and ODP. That looks true. I see. Yeah. Okay.
Yeah, I think that those two are now similar.
All right, I'll check one more angle, but yeah, it looks like there's a good chance that that's true. Oh, but those add up to 90, so yeah, they're similar.
Then we actually have a spiral similarity. This looks really nice.
Yeah.
Oh, actually, no.
It's not a spiral similarity about like 1 point, because like E and B are not the same point, but and also you have to reflect it. Like it's
Yeah, it is not a spiral similarity.
yeah. But I mean, the right angles I think are not hard. The right angles are easy to prove. We just have to show the ratios.
And yeah, this is equivalent to the problem. If we know that, then we can show that we have the cyclic quad.
Then we know that RPOQ is cyclic.
Yeah.
Interesting. All right. So yeah, maybe somehow using ratios. So let's see. So what do we know about the length QD? Or sorry, the length OD. So OD squared, that's the power of O with respect to that circle. Maybe if we could show that these two, like I wonder if these two quadrilaterals are homothetic. Oh, they're not going to be homothetic because AX and M are not collinear. Although they, maybe they are. Like, yeah, let me see. Sorry. I think AM and that point. Yeah. It looks like, yeah, like AM passes through the intersection of these circles. And that kind of, actually that's obvious because where the two circles intersect, we have one right angle and another right angle, so they're going to be collinear. QER and ODP. That's what we want to show. I wonder if the whole trapezoids are similar. Probably. Like trapezoid XQER and XODP. I think it's equivalent to showing that. Yeah, we can show all the angles in those trapezoids are equal. We just have to show that the lengths are in the right ratio. That's the hard part.
Maybe you can take down the things that I made you draw up so we can see clearer.
Say that again?
Maybe you can take down points K, L, N.
Oh, this circle?
Because it's like not really useful.
Okay. So yeah, we want to show these are similar trapezoids, XODP and XREQ. What if we let those intersect so that instead of similar trapezoids, we can get like similar triangles? So it's the same. Like it's the same as showing that this angle equals this angle. But that would be true just because these are right angles. So let me think about that.
Yeah, I think it's not sufficient to show that those are equal angles.
Yeah, no, you're right. It's not sufficient. Because PX could be like way out here, but then if we extend it, we would get a similar triangle. So, yeah. ODP and QER, that's what we want.
Does XA bisect the angle PXQ?
Let's see. It looks like it might. It looks very likely.
I mean, I might be crazy, but I think that's sufficient to show.
Okay. Yeah, it looks like XA bisects PXQ. So we know it lies on the A bisector. I mean, that's the same as showing that this right here, that's the same as showing this is a kite. Is that really true? So this is an angle bisector and these are right angles. So yes, this is a kite. And then from there, yeah, that means this is an angle bisector. And so you're saying that's sufficient. Yeah, because basically we have two trapezoids where all the angles are equal and where one of the diagonals is an angle bisector. So they have to be similar isosceles trapezoids. I like it. I think that does it, right?
I think so.
Yeah. Okay. So we added in so many points. I'll just say label the points as shown.
Okay, so like I think the easy way to say this, or like write this down, is that we see that by this angle bisection, XOD and XRE are similar.
Oh yeah.
And then XQE and XPD are similar. And in both cases, the ratio of similarity is lambda.
Yeah.
But in one case, it's like 1 over lambda, and then XO times XQ must be XR times XP.
Yeah. So yeah, it makes sense. So all right, so I'm going to type it up. I mean, I think if XOD is similar to XRE and XPD is similar to XQE, then you could say the whole trapezoids are similar. And I guess the ultimate proof of that is algebraic, like you said, but I think the viewers would kind of know how to do that. So so yeah, what do we have to prove and what do we know? Let me start from the beginning. So PX is perpendicular. Okay, so AIXG is a kite with two right angles. Two right angles. And that means that angle IXA is angle GXA. And that means that angle QXE is angle PXE. Okay. And then from there, we know that OXD is similar to XRE. But yeah, what do we have to prove? So I think I mean I guess we have to show that MD is perpendicular to XQ. But I don't think that's hard. Like, well, so we didn't. So for part I, I'm just going to write a quick proof. So since M is the point of BC and BD is parallel to CE, M is equidistant to lines BD and CE. And so that means that MD equals ME. I mean, I guess it's, let's see. So, I mean, M is the same distance, but I mean, I feel like there's one other thing too that we probably have to say there.
Sorry, what do you want to prove now?
Sorry, I thought it was really obvious that MD equals ME, but we did need to use like so M is equidistant to these two lines. I get that. But then how does it follow from that MD equals ME?
Well, DE is also perpendicular to these two lines.
Oh,
So
yeah.
if we were to
That's right.
project M orthogonally to the lines, then it's obvious.
That's right. It's because DE is perpendicular to both lines. Yeah. Yeah. All right. All right. So yeah, after projecting it, okay. So then for part 2, we have this, and okay. So I mean, basically, we wanted to show MD is perpendicular to XQ. I feel like there's a couple things that are easy, that are not hard to prove, but that we might have just kind of assumed. But all right, I'm just typing up. I'll just type up what I know so far. So so this implies that XOD is similar to XRE. And PD is similar to XQE. And these together imply that XODP is similar to XREQ. And so that's kind of how we get XR times XP equals XO times XQ. So I'll write it like this. So that means that XR over XQ is XO over XP. And that means that XR times XO or XR times XP is XQ times XO. And that implies that X lies on the radical axis of those two circles. I'll just finish it. XM is the radical axis of okay. So the only step I left out, I think, like 0.0 So we could let MB meet the circle at O, and then it's kind of obvious that that's a right angle. So point E is in the problem. We know EQ is perpendicular to AB, and we know E, what else do we know about? And then we want to show that these are collinear with point G. I think it's easy enough to prove the rest. We'll just move on to the next problem, but I think the viewers would be able to figure it out. But yeah, it was a nice solution. Okay. So this problem actually uses, it looks like, so we could do either the riddle or the middle riddle. Which do you guys want? This looks like it uses a previous IMO problem. Because it's like, this has a circle through points B and C. That's like tangent to the end circle. And there was like a IMO problem and a video on my channel that has that. So we could do this one or we could do this one. What do you guys prefer?
I prefer the easier one.
The easier, okay. So we have a triangle ABC. And E and F are on AB and AC. So that EF passes through the circumcenter of ABC. All right. So this is O. Let's make it a taller triangle. So that E, well, we have to draw like a ray. So this is E and F. And when we reflect A over EF, that's going to lie on the circle because EF passes through O. Because yeah, basically if you extend EF to hit the circle, it makes a diameter. So if you reflect A over that, it has to lie on the circle. And then A prime EF. So basically, yeah, this is a kite right here. This circle intersects AB and AC again at 2 points, X and Y. So this is X. And this is Y. And we want to show XY passes through a fixed point. So if I show the trace of this, then we're saying as I move E and F around, it passes through a point. And I wonder if that point is just the orthocenter. It looks like it. So let's see. Let's draw the orthocenter. I'm going to no longer show the trace. Yep, it's the orthocenter. Okay. So how do we show that those are collinear? I'm going to hide it. Let's just check that that's actually the case. Yes. It looks easy. These are perpendicular. So how to show we know AO and AH are orthogonal. I wonder, and we know AXY and AEF are similar. So basically we want to show that O and H are corresponding points on triangles AXY and triangle AEF. So I guess another way to say this is in triangles AXY and AEF, we want to show the similarity ratio is AH over AO. That's another way to say it. So I guess another way to say it is we want to show XY over EF is AH over AO. And also AH, maybe we can take advantage of this. AH is twice OM. So AH over AO is 2OM over AO. So maybe we could find similar triangles somehow. Wonder what happens if we reflect X and Y over this line. They lie on those two. I don't know what we do with that.
So what is the center of homotety that takes AXY to A prime EF?
Oh, interesting. Because yeah, those, I didn't even think about that. That's a good point. That should lie on A prime. Or sorry, maybe I'm not doing this right. Well, I guess they're similar, but they're not homonyms. So like a spiral similarity that takes one to the other.
Yeah, right.
So yeah, to find the center of the spiral similarity, so I should know this, but how would I sorry, how would I do that? Find the center of the spiral similarity. Do I just take the circumcircles of AXY and A prime EF? Or is it like, I forgot how to do this. I know it's really basic, but yeah, how do I find the center of that spiral similarity?
I have to think about it for some seconds as well, but I mean, I mean, it has to be just some Mikhail point of segments XY and EF. So, yeah, maybe.
So like the intersection of all these circles, is it like this Mikhail point or?
Yeah, I guess it should be. Or,
And I don't think those concur. Yeah, let me think a little bit more about. Is AM perpendicular to XY? No, it's close, but. Okay, so let's think about this a little more. So as we change E, basically we're saying that as we move E around, EF over XY stays the same. I wonder, let me try something. I wonder if AOM is like 180 minus this. I don't think it is. No. Maybe. Let's see. It's not that. And
so wait, are we just like, I mean, we do know that XAH equals to OAF, and we know that the big triangles are similar. We just don't know if O and H are corresponding, but they must be. Like, what is going on?
yeah, well, we don't know that X, H, and Y are collinear. I just drew that, so maybe that's yeah. Yeah, we don't know that that segment exists. Or that H lies on it. But if we like, yeah, if we could show that XY over EF equals AH over AO, then that means that H lies on it. So, I mean, it's the same as saying that the ratio of these two circles right here is ratio of their radii is AH over AO. So yeah, I wonder if there's anything special. So GXY is similar to GBC. That's a spiral similarity. So there we could get, from that we could get like XY over BC. So XY over BC is the ratio of the radii of this circle and this circle. And can we get EF over BC? Well, then we'd have to draw. So for EF over BC, what if we maybe we could use the power ratio lemma, because these two circles both pass through XY. So is there some other circle that passes through XY? Maybe these are collinear? No. Sec, be right back. All right, let's see. I'm back. Maybe we want to use that the reflection of H over BC lies on the big circle. Maybe that would help. I feel like there's probably a super simple solution to this, but super simple solutions are hard to see often, so. Because we need to use that this is the orthocenter, not just that it, you know, we have to use something specific to the orthocenter. Like maybe we could try reflecting this circle about BC or something. Then we're saying y, h prime, and x prime are collinear. Oh, and are they also collinear with a prime? It looks like it. So if we could show y a prime, if we could show y prime a prime and h prime are collinear, then by the same argument x prime a prime and h prime are collinear, and then I think that would solve the problem. Yes. Okay. I think that helps a lot. So all we need to show is that if you reflect y over BC, then y prime, a prime, and h prime are collinear. I feel like that's an easier problem. Well, h prime is always going to be in the same place no matter where e is. A prime is going to move and y prime is going to move. So all we have to show is that we need a showing a y h prime is h prime a prime. So h prime a prime is h prime a prime, which is like a b a prime. Or
Could you draw the orthogonal projection of a prime to BC?
yeah. Yeah, so we don't even really need the orthocenter for what you just drop the perpendicular from A to BC and you let it meet the circle at this point, and then you draw A prime, and then you draw Y prime. You want to show those are collinear.
So x prime and y prime are reflections over BC, right?
Right. We don't even really
And h prime.
Oh, sorry, what?
H prime is the reflection of H over BC.
Yeah, which is also just the perpendicular from A to BC where that meets the circle.
Yeah, right. Okay. It just looked like it wasn't on the circle, but okay.
But yeah. So all.
How about you reflect A prime instead of X and Y?
Let's see. So if I reflect A prime instead of X and Y,
Then you want to show it is on XY.
Yes. Yeah, that would work too.
Yeah, so the reason I wanted I is because now a prime prime is equal to the vector a prime prime is equal to 2 times di.
2 times AI.
2 times di. So like we reflected a twice, and now it's just a translation of a.
If you reflect something twice, then it's like a translation. Yeah, we reflect it, and then we reflect it. Oh, di is like parallel to a prime. I see what you're saying.
And the reason this looks so good is we know that di is parallel to a prime and half of it, and also ah is parallel to om and twice the size of it.
AH is twice OM. So yeah, it almost feels like that might solve it. So yeah, I could probably get rid of this for the time being. Oops, sorry. So yeah, and I could probably get rid of this too. So we just want to show the reflection of A over BC lies on XY. And I think that's the same as showing that XY, BC, and AH prime concur. So really, I think maybe this is just, yeah, by the radical axis theorem. Well, yeah, that's just the radical axis theorem, right? Am I missing something? Maybe so we have these two are XY. Oh no, that would be AG. That would be like saying that these concur, would be the radical axis theorem. Maybe we can make it work. I don't think EF passes through that point. No. But it seems like there should be a way to show these concur. Maybe we could start out doing it this way. And then, wait, what am I doing? XY, AG. So we know those concur. We have to show that these concur. So yeah, maybe it's just angle chasing, because let's think about it. We just need to show that this angle is equal to this angle. And this angle, so this angle, it's like the angle that XY makes with AH prime. Okay, so the angle that XY makes with AH prime is going to be the same as the angle that AO makes with EF, because they're both like isogonal. So to me, it almost feels like an angle chase should do it. We just have to write it out. So, all right, I'm going to delete these. It feels like angle chaseable. So if we just need to show XY and AH prime make the same angle with BC. And then from there, well, actually, maybe now I'm getting confused again. Does IB pass through the orthocenter? No. So I know this point exists. I'm going to start out drawing it. Oh, and once we know that point exists. Oh, I was going to try to show those isosceles, but that's not true. I feel like we did this before on my channel. I'm sure we have, but like so. Yeah, we could draw in the orthocenter and then try to show. So there's two ways we could try to show X, Y, and A prime are collinear. Or we can try to show why the orthocenter and A double prime are linear. What if we try to use this circle? Can we use the radical axis theorem with this circle? So this would mean yeah, I think it's going to be a little bit hard. It seems like there's got to be a way to show that these concur. So let me think about it. So yeah, let's say we don't know A double prime Y is on this yet. We just want to show X, Y, B, C, and A prime H prime concur. What we could do.
You calculate the angle with which lines AB and A prime H prime make.
A, B, and A prime H prime?
Yeah.
Okay.
Since you can kind of get the angle AXY.
Okay. So basically calculate angle AK A prime.
Maybe. Yeah, that is equal to AH prime A prime minus BAH prime.
Okay.
And BAH prime, we know if it is just 90 minus B.
Yeah.
And AH prime A prime is AE. Actually, no, it is ABA prime. Do we know that angle?
Okay.
Maybe we can split it in like it is angle B plus angle A prime BC.
So I guess ultimately, are you trying to show that these concur? Is that kind of what you're trying to show?
Well, yeah, but what angles could we get so we would know that those concur? Could we get some thing with angles in order to prove that those concur?
Yeah, because it's not enough to show that this angle equals this angle, unless we define a double prime. I mean,
We will want to show that those two lines are symmetric with respect to BC.
yes.
So that would be some things with angles probably.
Or I was thinking the radical axis theorem maybe, because X, Y is the radical axis of these two, but. I'm not sure. All right, well, I feel like we were pretty close, but we're out of time. So thank you both for staying around and working through these problems. And for everyone watching on YouTube, thanks for watching. So if you want to join us in a future session, feel free to email me at mgreen801@gmail.com. We meet every Sunday at 8 a.m. US Central Time. So thanks again and have a great day.